Section 9.3, Reactions in Aqueous Solutions. The objectives of this lesson are to describe aqueous solutions, write complete ionic and net ionic equations for chemical reactions in aqueous solutions, and predict whether reactions in aqueous solutions will produce a precipitate, water, or a gas. Some vocabulary review will be solution, and some new vocabulary you'll come across is aqueous solution, solute, solvent, complete ionic equation, spectator ion, and net ionic equation. You read in Chapter 3 that a solution is a homogeneous mixture. Many of the reactions discussed in the previous section involve substances dissolved in water. When a substance dissolves in water, a solution forms. An aqueous solution contains one or more substances called solutes dissolved in the water. In this case, water is the solvent, the most plentiful substance in the solution. Although water is always the solvent in aqueous solutions, there are many possible solutes. Some solutes, such as sucrose or table sugar, and ethanol or grain alcohol, are molecular compounds that exist as molecules in aqueous solutions. Other solutes are molecular compounds that form ions when they dissolve in water. For example, the molecular compound hydrogen chloride forms hydrogen ions and chloride ions when dissolved in water. An equation can be used to show this ionization process, where hydrogen chloride breaks down into hydrogen ions and chloride ions. Compounds such as hydrogen chloride that produce hydrogen ions in aqueous solutions are acids. In fact, an aqueous solution of hydrogen chloride is often referred to as hydrochloric acid. And we'll read more about this in the acids chapter. In addition to molecular compounds, ionic compounds might be solutes in aqueous solutions. Recall from Chapter 7 that ionic compounds consist of positive ions and negative ions held together by ionic bonds. When ionic compounds dissolve in water, their ions can separate, a process called dissociation. For example, an aqueous solution of the ionic compound sodium hydroxide contains sodium ions, or sodium cations, and chloride anions. When two aqueous solutions that contain ions as solutes are combined, the ions might react with one another. These reactions are always double replacement reactions. The solvent molecules, which are all water molecules, do not usually react. Three types of products can form from the double replacement reaction: a precipitate, water, or a gas. Some reactions that occur in aqueous solutions produce precipitates. For example, recall from section 9.2 that when aqueous solutions of sodium hydroxide and copper 2 chloride are mixed, a double replacement reaction occurs in which the precipitate copper 2 hydroxide forms. Now, precipitate is just another word for that when you mix two aqueous solutions together, you're usually just going to get a solid out of that reaction. We've heard the word precipitation before, where water falls from the sky. Precipitates will usually fall out of solution in the form of a solid. Note that the chemical equation does not show some detail of the reaction. Sodium hydroxide and copper 2 chloride are ionic compounds. Therefore, in aqueous solutions, they exist as sodium cations, hydroxide anions, copper 2 cations, and chloride anions. When their solutions are combined, copper 2 cations in one solution and hydroxide anions in the other solution react to form the precipitate copper 2 hydroxide. The sodium ion cation and the chloride anion remain dissolved in the new solution. To show the details of reactions that involve ions in aqueous solutions, chemists use ionic equations. Ionic equations differ from chemical equations in that the substance that are ions in solution are written as ions in the equation. Look again at the reaction between aqueous solutions of sodium hydroxide and copper 2 chloride. To write the ionic equation for this reaction, we must show the reactants, sodium hydroxide in aqueous form and copper 2 chloride in aqueous form, and the product, sodium chloride in the aqueous form, as ions. An ionic equation that shows all of the particles in solution as they exist is called a complete ionic equation. Note that the sodium ions and the chloride ions are both reactants and products. Because they are both reactants and products, they do not participate in the reaction. Ions that do not participate in a reaction are called spectator ions and are not usually shown in ionic equations. Net ionic equations are ionic equations that include only the particles that participate in the reaction. Net ionic equations are written from complete ionic equations by removing all spectator ions. For example, a net ionic equation is what remains after the sodium and chloride ions are crossed out of this complete ionic equation. Only the hydroxide and copper ions are left in the net ionic equation, as shown. Let's go ahead and write the chemical, complete ionic, and net ionic equations for the reaction between aqueous solutions of barium nitrate and sodium carbonate that forms the precipitate barium carbonate. So we're given the word equation for the reaction between barium nitrate and sodium carbonate. All right, we must determine the chemical formulas and relative amounts of all reactants and products to write the balanced chemical equation. To write the complete ionic equation, you need to show the ionic states of the reactants and products. By crossing out the spectator ions from the complete ionic equation, you can write the net ionic equation. The net ionic equation will include fewer substances than other equations. So by starting out with the chemical equation for barium nitrate and sodium carbonate in the aqueous forms, we form barium carbonate, the solid, or the precipitate, as well as aqueous sodium nitrate. Okay. So now what we're going to go ahead and do is we have to go ahead and balance out this chemical equation. And when we go ahead and balance out this chemical equation, we need to then go ahead and break it up into its ionic equation. Now notice how you have two nitrates in barium nitrate. So we have to go ahead and put the 2 in front of the nitrate on the reactant side. The same thing goes for the sodium. We have 2 sodiums in sodium carbonate, so we must put the 2 in front of the sodium cation on our reactant side. And the same thing goes for our product side. Now we go ahead and cross out the spectator ions to form the complete ionic equation, and whatever is left over is what we call our net ionic equation. Go ahead and pause this video so that you can write the chemical, complete ionic, and net ionic equations for the following reactions that might produce a precipitate. If no reaction occurs, write NR. So here are the answers for 35 and 37. Just a little errata. This iodide looks crossed out, but it was meant to be meant to be in play. It is not a spectator ion. Another type of double replacement reaction that occurs in an aqueous solution produces water molecules. The water molecules produced in the reaction increase the number of solvent particles. Unlike reactions in which a precipitate forms, no evidence of a chemical reaction is observable because water is colorless, odorless, and already makes up most of the solution. For example, when you mix hydrobromic acid with a solution of sodium hydroxide, a double replacement reaction occurs and water is formed. The chemical equation for this is shown, where hydrobromic acid reacts with sodium hydroxide to form liquid water and aqueous sodium bromide. In this case, the reactants and the product, sodium bromide, exist as ions in an aqueous solution. The complete ionic equation is shown. But if you look carefully at the complete ionic equation, the reacting solute ions are the hydrogen ions and the hydroxide ions, because the sodium ions and the bromine ions are both spectator ions. If you cross out the spectator ions, you are left with the ions that take part in the reaction. So the equation is the net ionic equation of hydrogen ions plus hydroxide ions give us water. Let's go ahead and write the chemical complete ionic and net ionic equations for the reaction of hydrochloric acid and lithium hydroxide that produces water and aqueous lithium chloride. The first thing we're going to want to do is go ahead and translate that word equation into a skeleton equation, and then go ahead and try and observe whether this needs to be balanced or not. In this case, it is already balanced, so we can just go ahead and break up all aqueous solutions into their constituent ions. Observe what ions exist on the product side as well as the reactant side, and then you're able to go ahead and cross them off. Once your spectator ions have been eliminated, what you're left with is your net ionic equation of hydrogen ion plus hydroxide ion yielding water. Go ahead and pause the video and go ahead and write the chemical, complete ionic, and net ionic equations for the reactions between the following substances that produce water. Here are the answers for 40 and 42. Just note for 42 how we were able to go ahead and reduce your net ionic equation by a factor of 2. A third type of double replacement reaction that occurs in aqueous solutions results in the formation of a gas. Some gases commonly produced in these reactions are carbon dioxide, hydrogen cyanide, and hydrogen sulfide. A gas-producing reaction occurs when you mix hydroiodic acid with an aqueous solution of lithium sulfide. Bubbles of hydrogen sulfide gas form in the container during the reaction. Lithium iodide is also produced in the reaction and remains dissolved in the solution. The reactants, hydroiodic acid and lithium sulfide, exist as ions in aqueous solution. Therefore, you can write an ionic equation for the reaction. The complete ionic equation includes all of the substances in the solution. Note that there are many spectator ions in the equation. When the spectator ions are crossed out, only the substances involved in the reaction remain in the equation. making the net ionic equation 2 hydrogen ions plus a sulfide anion, giving us hydrogen sulfide gas. In that reaction, in some reactions, carbon dioxide gas will be produced and bubbled out of a solution. And that's probably what we would observe in this chemical reaction as well, the production of bubbles. A reaction similar to one between vinegar and baking soda occurs when you combine an acidic solution and sodium hydrogen carbonate. In all cases, 2 reactions must occur almost simultaneously in the solution to produce the carbon dioxide gas. One of these is a double replacement reaction, and then another could be a decomposition reaction. For example, when you dissolve sodium hydrogen carbonate in hydrochloric acid, a gas-producing double replacement reaction occurs. The hydrogen in the hydrochloric acid and the sodium in the sodium hydrogen carbonate replace each other, and in doing so, sodium chloride is the ionic compound, and its ions remain separate in the aqueous form. However, as the carbonic acid forms, it decomposes immediately into water and carbon dioxide. Let's go ahead and write the chemical complete ionic and net ionic equations for a reaction between hydrochloric acid and sodium sulfide, which produce hydrogen sulfide gas. You are given the word equation for the reaction between hydrochloric acid and sodium sulfide. You must write the skeleton equation and balance it. To write the complete ionic equation, you need to show the ionic states of the reactants and products. By crossing out the spectator ions in the complete ionic equation, you can write the net ionic equation. Now, in the word equation, they told us what our reactants were, but only one of the products. I think you could be able to infer, doing a double replacement reaction, that you're also going to go ahead and create sodium chloride as well. In doing this, right now we need to go ahead and balance it, which gives us a 2:1:2 ratio. And because we have aqueous solutions, we are able to go ahead and split them up into their ions, but we leave the gas as is. We do not go ahead and split up the gas. Notice what your spectator ions are, and you're able to go ahead and cross them out to go ahead and give us the remainder, your net ionic equation. Let's go ahead and pause the video so that you can write the chemical, complete ionic, and net ionic equations for the following reactions. So if we take a look at 45, right, just to kind of point out that what we would expect is that as our products we will get carbon dioxide and water, but how we get the carbon dioxide and water is that what we really get is the reaction products of potassium perchlorate and carbonic acid. That carbonic acid is going to go ahead and decompose to give you carbon dioxide and water in the end. Recall that when you combine an acidic solution such as hydrochloric acid and sodium hydrogen carbonate, 2 reactions occur, a double replacement and a decomposition reaction. These reactions are shown in the figure 920. The 2 reactions can be combined and represented by one chemical equation in a process, similar to adding mathematical equations. An equation that combines two reactions is called an overall equation. To write an overall equation, the reactants in the two reactions are written on the reactant side of the combined equation, and the products of the two reactions are written on the product side. Then any substances that are added that are on both sides of the equation can be crossed out. In this case, the reactants in the overall equation exist as ions in aqueous solution. Therefore, a complete ionic equation can be written for the reaction. Note that the sodium and the chloride ions are the spectator ions. When you cross them out, only substances that take part in the reaction remain. The net ionic equations show both water and carbon dioxide are produced in the reaction. Section 9.3 Summary. In aqueous solutions, the solvent is always water. There are many possible solutes. Many molecular compounds form ions when they dissolve in water. When some ionic compounds dissolve in water, their ions separate. When two aqueous solutions that contain ions as solutes are combined, the ions might react with one another. The solvent molecules do not usually react. Reactions that occur in aqueous solutions are double replacement reactions.